Okay. I hit Aufzeichnung, and therefore it should be working. Okay, so try one of recording a Zoom session and then posting to YouTube afterwards. Let's see how that goes. So we're working on the first question that I sent you guys in the packet. It was on WhatsApp. So if you want to open it up there, that'd be good. Or if you printed it out, that's cool too. They're giving us an equipotential diagram for two charges. And let's just read through the question first of all, just to make sure we know what's going on. Is the diagram nicely visible on your screen? Maybe make it a little bigger. I can high tech roll the board closer. There we go. There we go. All right. So the dots in the figure above represent two identical spheres, X and Y, that are fixed in place with their centers in the plane of the page. Both spheres are charged, and the charge on sphere Y is positive. Okay, so we're going to draw that on here, that this one's positive. Put that right there. That's charge Y. This is Y. There we go. Okay, so Y is positive. Nice. So there we go. They don't say whether these are conducting spheres or non-conducting spheres. So we're just going to treat them as charges. Okay, they say spheres, but okay, but they don't have any other information. So we're just going to assume there's a charge there. All right, so let's take a look. The lines are iso lines of electric potential, also in the plane of the page, with a potential difference of 10 volts between each set of adjacent lines. The absolute value of the electric potential on the outermost line is 50 volts. Okay, so they gave us information that this is 50 volts. Okay, and then obviously it comes all the way over here, and this is also 50 volts. We're just labeling what they told us. Everything makes sense so far? Yeah?
Couldn't it also be negative? Couldn't it also be negative because it's this absolute value?
Oh, interesting. You're right. It could be negative. We're getting ahead of ourselves. Good. So, actually, that's a good point. That was Sam, right? Nice point, Sam. This is a positive charge, right? So over here, these should be positive potentials, unless something goofy was going on. For some reason that this charge was so powerful that was overwhelming this negative charge's potential or something, but it looks that pretty clear that based on this being positive and the way the structure of this is, that this actually would have to be a positive potential. But you're right, Sam, I actually missed that. You're right, it could be negative, although that would be hard to explain based on the shape of this thing. Does that make sense?
Mm-hmm.
Okay, good. So if that is positive, and it is positive, and this is a positive charge, that means as we're getting closer to this positive charge, what would happen to the potential as we get closer? Gets higher or bigger or smaller?
Bigger.
Bigger, right? Because, and this is just a kind of a reminder about the equation for the potential of a point charge, and the kind of everything comes back to our little grid of four things: electric force, electric field, electric energy, and electric potential. And you kind of always have to come back to that idea of what kind of object are we dealing with. We're dealing with potential, so this is a property of space, and we're dealing with potential, so it is a vector or a scalar?
Scalar.
It is a scalar. Potential is a scalar, so it just has a number, it doesn't have direction. Electric field is a property of space, but it has a direction. Okay, so this is 50 volts. They get bigger, and they tell us they get bigger by 10. So here we go. This will be 60 volts, right? And then, of course, it also means it's 60 volts over here, right? And then this one's 70 volts, right? This one's 80, right? And now it's a little tight here, but we can get that on there. So this one's 90, and this one's 100 volts. Make sense so far? Okay, we just kind of used a little bit of reasoning, but otherwise we're just writing down what they told us. Okay, so if we look at this, there's positive values here for the voltages, potentials. We had a positive charge here. Now we have another charge here. What's going on over there? 70 volts there, 80 volts there, 90 volts there, 100 volts there, plus 100 volts there. So what kind of charge is this? Is it a positive charge or a negative charge?
Be positive.
It has to be also positive, right? Because this charge by itself, this distance away, would be creating negative, would be creating a much lower positive voltage, right? It's 90, 80, then it would be 70, 60, 50. So if this was a negative charge, it would create a negative potential here, or at least a smaller potential than these values here that they would be, right? So this has to be a positive charge as well. Now, while we're just thinking about it, we haven't looked at the questions yet. What would you say about the magnitude of the charge? And this is a nice little trap that they set you based on this. Which of these charges is bigger in magnitude? They're both positive based on the shape of the potentials, equipotential lines, but would the X charge be bigger or smaller?
Smaller.
It would be smaller. And the reason that's confusing, and I'll just address it directly, is that it looks to you guys, and with all due respect, okay, just say students in general, it looks like this charge doesn't have really a lot going on around it, right? It's like, oh, there's no potential here. There are no lines here. And there's a bunch of lines here. So these lines that are bunched up here indicate to me that there's a big charge here. But that's actually not the way to look at it, okay? This charge here does have equipotential lines next to them. We're just not drawing them in because the biggest potential line we're drawing is 100 volts. Okay, so as we get closer to this Y charge here, we could just draw 110, 120, 130, 140, 150, 160, and when we get to the distance and the same distance that we have here over next to this charge, we would expect those lines to be maybe 200 volts, maybe 300 volts, I don't know, but certainly much bigger. And that's why it looks over here like there's not much going on, but there is much going on just further away. And because the distance is bigger to the 100-volt line, you can think about it that way, this charge has to be a bigger charge. Or charge Y is bigger than charge X. Okay, good. So we've reasoned it out, and we've got pretty much everything settled in and thought about what these potential are. And now we can answer the questions they ask us based on having understood the situation. So they're asking for the values for potential A and potential B. Totally cool. We got that already figured out. This one's 60 volts, and of course, B would be 80 volts. We didn't write that there, we just wrote it over here, but that's the same potential as there. So we've answered part A, that the potential at point A is 60 volts, and the potential at point B is 80 volts. Okay, so next they're asking us for what the charges are looking in terms of signs. They're both positive, we decided that. We also agreed that the charge for X is smaller. So charge X is smaller than charge Y. Good. We've got that figured out. And we kind of spoke the explanation out. We said that the reason for us believing this or knowing this is because for the same distance, like here to here, to get to the 100-volt potential, this is a bigger distance. So if R is bigger, then Q has to be bigger as well to create the same potential at this distance compared to this closer distance at which this charge creates that potential. Now, technically, it doesn't create this potential by itself. There is an effect that is coming from the other charge, but it's rather small at that close distance to this charge and the close distance to this. And that's why this is pretty much circular anyway, and this is also pretty much circular. So for this, just for a qualitative analysis, we can just say, okay, well, charge Y is creating equivalent potential at a bigger distance because R is bigger. That means Q has to be bigger to create the same potential. Okay, now they're going to take this question and reach back to mechanics. Just to remind you about that, they are allowed to do that. They can ask something during the E&M test about mechanics, that's allowed. And they say, okay, let's say we have two charges here. Well, they have mass as well because they're spheres of some kind, styrofoam, whatevs. So these spheres have mass as well, and they want us to think about what happens. And they're saying the ratio of the masses is the same as the ratio of the charges. Good. And they're also then telling us that the gravitational isolines will look in the same shape. Okay, but of course, for them, for gravitational potential, it wouldn't be measured in volts. Okay, because the important difference, and I'll just remind you of that. So electric potential is related to electric potential energy through this relationship that electric potential energy is Q times V. So if I were to place a charge at a potential line, like right here, for example, then its potential energy would be its charge times 50 volts at this point. And of course, as a consequence, that means because the energy unit is joules, right? And the unit for charge is coulombs, right? That means that a volt, which is the unit of voltage or potential, that needs to be a joule per coulomb. And we don't constantly emphasize this, but it's a good reminder for us that that's what that is. A volt is a joule per coulomb. So a volt, the unit of potential, sorry, annoying, is a joule per coulomb. So electric potential unit is joules per coulomb. Now, gravitational potential, we could do the same thing we did here. And we can say, okay, well, this is electric potential, but gravitational potential behaves the same way, just as gravitational field, gravitational force, gravitational potential energy, and gravitational potential behave in the same way as well. So, and we have equivalent relationships, okay? So I'll just remind you guys about those. It's kind of a backflash right now. So we have gravitational force, right? And that's minus m1 m2 g divided by r squared. Technically, we've got the little r hat on the end there, right? That's the electric gravitational force. And it's really the same relationship as the electric force, right? With the only difference that obviously we've got charges. We've got then K rather than G. But otherwise, very equivalent relationship. Yeah, and the minus sign is missing, right? Right, because electric forces likes repel, opposites attract, and for gravitational forces, we only have likes, and likes attract. Gravitational forces, likes attract, that causes the negative sign. And down here, for electric forces, likes repel, so there's no negative sign right there. Okay? But so that means everything about gravitational forces behaves just the same as electric forces when you do the math in terms of figuring out gravitational field, gravitational potential, and gravitational potential energy, except there's a change in the minus sign. So for example, we have this thing, which we call gravitational potential, and there would be an equivalent electric potential. Gravitational potential would behave the same, but it would have G M over R and a minus sign. So that is the gravitational potential created by a point mass. Okay, how are you guys doing? Is that making sense?
Mm-hmm.
Okay. Okay, that was just one. Mm-hmm. Can I get some more or ah or some kind of expression of disbelief and or joy? If you don't want to speak on tape, that's cool too. So, but at least maybe one other person can either say, yeah, that makes sense or something.
I don't fully get the last point.
Okay, good. So, so coming back to hello. That's funny. Sorry, I had fun with that. Okay, so the four quantities that we're talking about, okay? I'm coming to a whiteboard here. So the four quantities we talk about, am I still on screen? No, here we go. So four quantities we're talking about are force, electric field. This is for electricity. Then we have potential energy. and we have potential. Always important to come back to these and remind ourselves, well, how are they related? Okay. Okay. So a few things here. First of all, force is related to electric field through just multiplying charge by electric field. Then you get the force on that charge. In the same way down here, electric potential energy is just, whoa, that's not pretty. I'm going to move that over a little bit. Is just equal to charge times potential. Okay, and a few other things we said was, okay, these things are vectors. Am I still on screen? Not really. Am I on screen? Shit, I can't see. There we go. There we go. So these are vectors. These are scalars. Okay. And then in these categories here, this is properties of particle. Like how much force does a particle experience? How much energy do particles have? And these things are properties of space. Meaning, what's the electric field at this point? What is the electric potential at this point? Okay? Does that make sense so far? Just a reminder about that?
Yeah. Makes
Okay,
sense.
good. And we also had connections between them in this direction. Okay, and the connections in this direction were that you could find the force from the potential here, and vice versa. You could work back and forth through a differential relationships. Okay, and maybe I'll choose a different color here. I don't know if that's confusing and or helpful, but I think it will be. So it's that, is that big enough? I think it is. Okay, good. So that the force is minus du dr. How quickly does the potential change? That is the force. Sorry, how quickly does the potential energy change? That is that. And the relationship in this direction is the equivalent because they're just related through Q. So of course, if we have this relationship here, we have the same relationship here. So we can say, okay, well, the electric field, and this is normally how we look at this, is equal to the derivative of dV. Okay, how quickly does the potential change is the electric field. Okay, so that's how these are connected. This is how these are connected. This is how these are connected. Whoa, I kind of trying to, okay, here we go. And these are how those are connected. So, but these relationships, where they really come from, are based on the force, right? We talked about force and the reason we end up with the relationships that we have for point charges is because the force equation is what it is, and we know what it is. It's Coulomb's law. Okay, so Coulomb's law says the electric force is K times Q1 times Q2 over R squared times R hat. Okay, that's the relationship for force, and then everything else flows from that because we can, you know, instead of taking the derivative from here to go there, we can integrate from here to go there. Okay, that's how we got there. Well, you can do the same thing here. You can multiply by Q to find, you can divide by Q to get electric field, and then you can integrate to get the potential of a point charge. So once you have the starting point of what kind of force there is between two charges, right? Then you can go here, you can go to these things by using the relationships that you have on the screen. Okay, and because this is so high tech, I love this. I'll roll this back. Okay. That works. And because we have the relationship that electric force is K Q1 Q2 divided by R squared. I'm on screen? Nope. There we go. Moving chair back on table. Man, it's like having a whole camera crew here. Okay, so here we go. And a little bit more. There we go. Okay, so times R hat. And just a reminder, R hat is just the direction of between the two, the force that's created there. Because the gravitational force is equal. Have you guys seen the, I'm sorry, have you guys seen the cartoon of Coulomb sitting next to Newton during the physics exam? Have you guys seen it? No. Okay, I think there's a no. So Newton on this little cartoon, this nerdy cartoon, is writing down his equation, right? This is Newton's little, that's what it says on Newton's paper. And Coulomb on his paper writes down this while he's looking at Newton's paper, basically copying off him like he's another physics student, which is kind of funny. Like Coulomb's a really smart guy, but we're making fun of him because it's just the same equation. That's what I'm saying. These two equations are the same equation, only that, of course, charges and masses play different roles. Masses are gravitational forces and charges are electric forces. So that's the only difference here. The constant is different. And then the only other thing that's different is the not negative sign, but otherwise it's exactly the same equation. So that's why we can make fun of Coulomb for copying off Newton, because like, whoa, that's like the same thing. Totally the same thing. The universal law of gravitation, this law, and Coulomb's law, boom, same equation. Not impressive, Coulomb. Just kidding. He's a really smart guy and he's dead, so I should be more respectful. Okay, that making sense so far? And then as a consequence, all this stuff we wrote down here, we can write the same stuff down for gravitational force in the same way, and gravitational field and gravitational potential and gravitational potential energy. And all the relationships that we have for electricity are the same relationships for gravity, with the only exception that there's a minus sign. Makes sense? Because when we do the integral, this minus sign will just be multiplied out, but everything else stays the same. Okay, so I have three options. Either I lost connection to you guys, or the explanation made total sense, or you're still like, oh my God, we're all gonna die.
Made sense.
Made sense? Okay, good. All right, good, helpful. Okay, cool, good. I think that was a good review of that thing. And again, this grid is like awesome, really, really, really important. And just a reminder that because they're doing kind of a different approach, right? Because we're not giving the exam in a room with your only having access to the equation sheet. You obviously want the equation sheet, but this time it's allowed and not at all illegal for you to have other equations written down. So if you look at the equation sheet and you're like, wait, where's the equation for the potential of a point charge? They don't have that. I don't know. I'm just making that up. So you get the idea. If you have other equations you found useful, just write them down. You're allowed to use those. And if that was totally obvious, sorry for wasting your time.
So this is like fully open notes?
It is fully open notes. It's open notes. It's even open internet. It is not open people. So you're not allowed to have contact with somebody else. You can't have another person in the room helping you. You can't go on a message board and type help current AP Physics C exam. Does anybody have the answer for one? You know, that kind of stuff. That's disallowed, and they will be looking online. They can't look everywhere. Obviously, if you WhatsApp somebody, shouldn't even tell you this. So, you know, don't do that. Don't do that. If they find out, they have threatened severe penalties. You know, I mean, really severe penalties, including not allowing you to take AP exams ever, not counting your essay, canceling previous SAT scores. I mean, stuff like that. It's like, holy crap. That's like, you know, death by college board.
If I have the AP Physics C exam book with me, I could use that, can I? Right?
Yeah. So the design is such, though, remember, it's 25 minutes and then it's 15 minutes for the two questions. So if you're like, all right, I'm ready to go, I'm going to read the book now. Like, no. I mean, 25 minutes, you won't have enough time to even read hardly anything. So it's going to be very tightly structured. And that's the idea that, sure, if you have the book open and you look at the things the relationship or a sample problem might be helpful, but they're going to create problems that are not like problems in the standard books. And they're going to give you, basically, it's going to be maybe somewhat helpful, but it's not going to be super helpful to have a book open. So I think it would be better for you to have the equation sheet and like some like limited notes, like 2-3 pages of additional equations, additional approaches, reminders about how to apply Gauss's law on a symmetrical, spherical, whatever, you know, those kind of things are helpful. If you're going to start looking at pages 127 through 189, you know, in 25 minutes, you can forget it because you're going to be in trouble. Okay, cool. All right, so let's come back to this and good. Okay, so now that we've talked about this, we can answer their question because they asked, so what if we look at two charges? Instead of two charges, we look at two masses. I'm gonna come closer again. They're closer here. Wow, this is so high tech. Should get this. No. Copyrighted. Okay, so now they're saying, what if we had two masses? What will be different? Well, let's think about that. Well, so first question is, why do the isolines have the same shape? Well, if we're replacing the two charges, or we now know the two charges also have masses which are in the same ratio, right? Okay. Well, because everything is the same about gravity as it is for electricity, including, and now I am back to this thing here, including that the equation for potential is really the same equation with only the electrostatic constant replaced with G, the charge replaced with M, distance is still R, and there's only a minus sign, right? It's the only difference. Otherwise, potential is the same. So we can expect that these lines would be the same shapes and they have the same separations, but these values here wouldn't be in volts, which are joules per coulomb. They would be in joules per kilogram, which is gravitational potential, fine. But they'd still have equal steps, but of course much smaller, okay? The differences here would be very, very small because gravitational force is relatively speaking a lot smaller. And the reason for that is that K, just a reminder, is 9 times 10 to the 9 Newton meters squared per Coulomb squared. That's showing up, isn't it? It is. And G, which is the gravitational constant, is 6.67 times 10 to the minus 11 Newton kilogram squared, Newton meters squared, sorry, meters squared per kilogram squared. So if you look at this, for the equivalent charge values that compared to gravitational mass values, it'd be a factor of 10 to the 20. So 1 kilo of mass compared to 1 coulomb of charge would have 10 to the 20 times less, a factor of 10 to the 20 less gravitational potential, right? Because that constant is in the equation, all right? Good. So, make sense?
Yeah.
Okay, good. So same shape, but the values would be much lower. And of course, the minus sign is in there too, so that's going to change the values here. So these would be negative values. Everything would be negative values for the gravitational potential. So let's see how they go on then. They say, all right. Right. Good. So 2. Now,
Wait, but this is hold on.
Yep.
But this would only be true if the masses are like the same as the charges, right?
They're in the same ratio, and they do say that they are.
Okay.
So this might be 5 coulombs and 1 coulomb, and then 5 kilos and 1 kilo, or 10 kilos and 2 kilos. Okay, it doesn't really matter. As long as the ratio is the same, we're good to go. So let's take a look.
All right.
So that's we're at A1, A2. Now we're coming to question. Is there no question B? Something happened there? Am I stupid? There's no question B, right? It goes right to C. Oh, well, whatever. Oh, they mislabeled or something. Interesting. Okay, so based on your answer, briefly describe one similarity and one difference between the electric and gravitational force exerted on the proton by the system of the two spheres. So we're going to now put a proton at point B. So we put a proton here. Okay, we place a proton at that location. all right? And we can figure out what's going to happen. So first things first, just talk about the electric situation. There is a proton here, and what will happen to this proton? Just describe it in words. On the electric force. What direction is the electric force on this proton?
Top right.
Top right, okay? So the electric
Or
force is going to be in this
perpendicular to that.
direction, okay? And because it is a proton, they're nice enough to give us a proton, it is in the direction of the electric field. And the electric field is perpendicular to the iso line, okay? And it points downhill, meaning to lower potential, which means that positive charges would have a tendency to move directly towards a lower position from a potential perspective. And remember, I kind of gave you guys the analogy of this is kind of like a altitude line on a mountain. So water tends to flow down slope. I don't know if you were a scout, they might have told you that when you were reading maps. So water flows in this direction normally because it flows to a lower altitude. And the same thing happens here. We're at 80 volts here. It's going to flow towards the 60 volt. Makes sense. And of course, you can also just look at positive charge here. That's the closer one. We can kind of ignore this one for this purpose. It'll repel this charge here. Makes sense. Okay, so it moves in that direction. Now, on the other hand, a mass here and a mass there, right? That would create a gravitational attractive force. Masses always create attractive forces. There are no repulsions, so there would be an attraction in this direction, which is along the same direction, but opposite in sign, because gravitational and electric forces are really the same. The only exception that there's a sign there, sign difference, the negative sign. Okay, so we reasoned it out, and we're going to look again at what they asked us. Briefly describe one similarity and one difference between the electric and gravitational forces. Okay, so you can do different things here. You can say the forces are in the same direction along the same axis might be a better explanation, right? Because the gravitational force will point in the, oops, lid broke here. Okay, and maybe use a different color, that's smart. So that red is the electric force because the diagram is confusing enough as it is. So let's use maybe black here. So let's go there. And the gravitational force will be in this direction, right? So the gravitational force would be in the other direction. It's not showing up super good, but it is in the same, along the same axis. Electric force goes this direction, gravitational force is that direction. So hey, we could just say that. They are along the same line, but they have opposite signs. So the electric force is to the top right, and the gravitational force is to the bottom left. That would work for me. I like that explanation. You could also say, although they didn't really say how big these masses are, because they could be like, well, what if this is Jupiter and this is, you know, Mars? Suddenly that gravitational force is really strong. But that's stupid, okay? I mean, I think in general, you could say that the electric force is most likely going to be bigger in magnitude. But technically, I don't know if they would give credit for that. Although in the laboratory, this would certainly be true. The gravitational force would be much smaller between or near two charged spheres compared to the electric force on that proton. Makes sense. You don't have to worry about gravitational forces when you're looking at atoms and molecules interacting. Okay, so that's that. We're now through part C. Okay, and we're a little bit low on time. We only have 6 minutes left, but I think we're making good progress. I really like what we're doing here. So part C asks, we did part C. Part D, at some time after being released from rest at point B, the proton has moved through a potential difference of magnitude 20 volts. All righty. So, so we started here, right? And then it's moved, of course, to this location right here. So it's moved from 80 volts to 60 volts. Okay, so it's moved to a lower potential. And at that location then, right, when it moves from 80 volts to 60 volts, let's kind of maybe, I'm gonna try this. I don't want to flip the, here we go. Use this thing here. All right. So kind of a little close up. So we have, here's 80 volts. There we have 70 volts. And should be spaced further apart then, 60 volts. Okay. So we just said we're going to release that proton at this location, right? Good. And then after a while, it's going to be here. What has changed beside its position? That's a hint. Okay. Not everybody at the same time.
Question.
The potential difference is negative 20.
Sure, the potential difference is
Or
negative,
I mean,
and it's moving, right? Good. So it's moving this direction. Good. So we've done work on this thing. It was not moving here. It's now moving there. Makes sense. It's got a potential difference of 20 volts. Makes sense. So this is called point B. It's moved to around point A. Good. So we can say that the work done here is equal to the kinetic energy change. And because the initial kinetic energy is 0, right? V0 is 0, K0 is 0. So work done is delta K, but it's also equal to K. It has K here. So is moving. Makes sense. Whoopsie. There we go. That works. Okay. So work done is delta K is equal to K. All right. So it also means this is equal to minus delta U. Make sense? Because work is delta K, but work is also equal to minus delta U. Yeah? And that comes from the conservation of energy that delta E for a conservative force is equal to 0. And of course, delta E in a conservative situation comes from changes in potential energy and changes in kinetic energy. Okay? Good. So it's now moving, and we can answer the question they had, which is specifically, determine the change in electric potential energy. Now you need to watch out here because they want you to express your answer symbolically in terms of Q, VA, VB, and VC. There's a little trick there. So even though they told you the potential difference is 20 volts, and they told you the charge, you could actually plug it in. You could be like, well, the charge of a proton is plus 1.6 times 10 to the minus 19 coulombs. The potential difference is 20 volts. I'm just going to take 1.6 times 10 to the minus 19 multiplied by 20. Boom, there we go. They say, no, we want the answer symbolically. Okay, sorry. So we have to go from W is equal to minus delta U, which is what they're asking here. Yep, good. So potential energy change. I want to find a spot I can write this. Let's write this here. Delta U is equal to the final here minus the initial. So that is Q, the charge, times UB minus QUA. Make sense? We're just writing it down what delta U is, which is what they've asked for. Correct? Yep. The change in electric potential energy. Always good to remind yourself what delta means. Delta is always final minus initial. Okay, so that's easy to mess up. Delta is final minus initial. This is the final position. That was the initial position. Make sure you remember that, and then that should be straightforward. And in this case, they are hateful. If you look at I did look at the key. They did not give you credit if you, for some reason, plugged in numbers. So you can write it like this, or you can use it. You write Q equals. Q. I screwed this up. You guys are nice, not saying anything. So this should be V. Sorry. So there we go. There we go. QVB minus QVA. Okay, correct? Good now? Sorry about screwing that up, but now we're good.
But shouldn't it be QVA first? Isn't A the final?
Oh shit, you're right. My fault. Yes, you're right. My fault. Yep. See, I even gave you a little speech about make sure this is the last to final. Yeah, it moves from point B to point A. So final position is A, initial position is B. So you're correct. So it's QVA minus QVB. Thank you, Sam. Good correction there.
Right, but But then it's also negative, so wouldn't you just flip them anyway?
Well, hang on a second. They're asking for the potential energy change. So they asked for specifically the electric potential energy change. That is this. The work done is the negative of this. Okay? So you're right. So work is minus delta U. That's correct. But delta U is this. So when we now write down this, we can rewrite it as delta U is equal to Q times VA minus VB, right? We can also write that the work done is the negative of that, which will be Q VB minus VA. Now, if you were asking for work, but the question itself asks specifically for the potential energy change.
Don't we need a negative sign in there?
We do not, wait, yeah, I did, I put it in here. See, I flipped it, sorry. Yes, there's a negative sign in here that flips these two around.
Oh, right, of course.
All good, Giannis, that's a good question. Okay, we are at the end of our time for today. It is 11:22. So I will record this now and I will hit the record button, the end recording, and then I'll see how whether it works to post this. It should, so anhalten, here we go.